Hi, my name is Dr. Austin Norby, and this is my presentation on the NopEmulator capability. So who am I? I recently received my PhD in cyber operations from Dakota State University. I've been working and supporting the Department of Defense for over 10 years, and I'm currently employed as the Director of Internal Research and Development for Bogart Associates. So what do I do day to day? Well, generally I write C, C++, Python, and assembly code while looking at different operating systems. This can include anything from reverse engineering, vulnerability research, malware analysis, and in general, software engineering standards, unit tests, and best practices in architecting new capabilities and solutions. So NopEmulator was a tool idea that I came up with during my doctoral program, and while doing the research, I noticed there's been a lot of research into detecting buffer overflow attacks at a binary level. Many different ways of implementing this, but the main ones I saw were network-based detection, where an IDS or an IPS would have a sort of detection capability that would look at a stream of bytes or a sequence of bytes and use that to determine does this packet contain an exploit. One of the main ways that it did that was by looking at the instructions. They broke it up into really three chunks for those byte sequences. You had the initial header or content or data that was needed as part of that packet. You had a NOP sled that transitioned execution from wherever the overflow took place to the actual execution of a payload. And then lastly, you finally had the payload. What I noticed with that is the NOP sled detection was fairly primitive. It looked for a series of hex 90 characters for intel, which is the NOP instruction. It looked for very specific instructions like a jump instruction at the very end, or it did simple things like, are these all valid byte sequences? Not necessarily is this an actual NOP sled. So with that, I got the idea, well, maybe we could improve on that. So I continued reading and doing the literature review, and I saw that there was also research for machine learning, and they would take the byte sequences and gather data related to that information and use some sort of machine learning classification approach and attempt to detect it. Now this works with varying levels of success based on the information you have and how you're attempting to combine that information into a classification decision, but the machine learning approach is not the way that I wanted to go. And lastly, there's detecting system calls. So similarly to the network-based detection and processing those bytes, detecting system calls really looks for, hey, does any of these byte sequences actually try to call something that could be an instruction? That really tends to point at, hey, this code is trying to run something, rather than this is just a meaningless sequence of bytes and we should ignore it. So being able to detect system calls could be very useful in determining, this is probably malicious, or this might be an exploit or a payload, we should look into this. The most related algorithm that I found related to this kind of research was called the stride algorithm. And the stride comes from, it takes strides of different lengths to find any NOP sequences in a stream of bytes. So again, this was one of those things I thought could be improved upon, and that's where NopEmulator came from. So how does stride work? Well, it looks for valid byte sequences. So it first checks, are these valid instructions? Are these sequences of bytes a series of valid instructions? If they're not, then they're not going to be able to execute, and it's not going to work, and that was probably something you can ignore. It also looks for a jump instruction at the end, the assumption being that all of that execution up to that jump sets up the register state to be in a place where when that jump is made to whatever code needs to be run, everything's set up correctly. The stride algorithm used the maximum execution length in order to determine, is the sequence of bytes an NOP sled? And what this means is it starts and it processes byte sequences, evaluating them, executing them, emulating them along the way, and looks for the longest sequence of bytes that could be a NOP sled, and uses that to determine, yes, this is or is not a NOP sled. So how does NopEmulator differ? Well, NopEmulator removes any length requirements. It uses the Ghidra emulation engine to emulate all of the bytes and instructions. So it really doesn't matter how long the sequence is. The length of the sequence will increase execution time, of course. However, there is no cap on that length. Like I said, it uses the Ghidra emulation environment. There's other ones out there. There's Unicorn, there's Anger, there's any QEMU. You can use different types of emulation environments. For this research, I opted to use Ghidra, as there's not been a lot of research published with Ghidra, and the culmination of this tool will be a research paper. Lastly, NopEmulator has many different types of analysis, and we'll go into that in the next slide. So how was NopEmulator implemented? Well, it was written in Java as what's called a Ghidra script. So the Ghidra execution engine, the reverse engineering tool, allows you to write scripts using its SDK that's built in to process all of the bytes that are in your project. So you can manipulate it based on instructions, based on bytes, based on P code, which is the intermediary language between the assembly and the high-level code that Ghidra uses. And you can manipulate that to help with your reverse engineering efforts. So the Ghidra script that I wrote, NopEmulator, the algorithm is split into 3 phases: initialization, emulation, and validation. The initialization phase is collecting all of the necessary information in order to set up a successful emulation using NopEmulator. This is going to be, what initial values do you want for your registers? What registers are you interested in looking at? Is there any length that you want to look at specifically? Do you want to look at all the options? Do you want to run different kinds of analysis? What is it that you need to initialize this execution environment in order to get the results that you actually want? The emulation step is exactly what it sounds like. This is where Ghidra actually emulates from wherever you selected using the initialization variables that you wanted in order to determine if the sequence is a NopSled. And then lastly, as validation, the validation is where we check, do we have a NopSled? So this looks at the state of the execution and determines, did anything change? When we started and when we ended, is there anything different about the current execution state? And if there isn't, we can say that that for sure is a NopSled. Now, if something does change, you have to make a decision as an analyst, as a reverse engineer. Is that change reasonable? Does that change matter in terms of what I'm trying to understand about this code? And that's where setting the configurations and the values in the initialization phase can be really helpful. The whole point of this script is not to be a one-shot magic pill panacea to understand. This is to help your analysis and determine, yes, based on my assumptions, based on the way I need it configured, this chunk of code, this potential NopSled, is or is not a NopSled. And there's multiple types of analysis that we can do for this. So you have a full start to end analysis. Is this entire thing a NopSled? You have picking your addresses. Hey, I just want to look from A to B and see if that code in there is a NopSled. You have the start to offset, and you say, well, I know I want to start here, and I want to look at the next 50 bytes, and we're going to see if that's a NopSled. You also have the longest, and this is similar to that stride's maximum execution length. The longest analysis looks for the longest sequence of bytes that is a NOP. So it goes through every start point and every end point, every permutation, and looks for that longest NopSled, if there is one. And then lastly, full analysis. Full analysis goes through every permutation. It labels every length that could or could not, or that could be a NopSled, and provides you with as much output and analysis as possible with the script. And keep in mind, it can be very verbose. So let's go ahead and jump into a demo so you can see how this works. Alright, welcome to the demo. We've already opened up Ghidra, so we're going to go ahead and open up a bit of shellcode that we want to analyze. We're going to import the file. We're going to take this conditional.nop2.bin. Since it's a raw binary, Ghidra can't figure out by default what language it was compiled in, so we're just going to tell it. In this case, the x86, 64, little endian, and using the Visual Studio compiler. We already used this for analysis once, so let's go ahead and just change it. We'll bring it up. So it says it's not been analyzed. That's fine. We don't need Ghidra to analyze using its default analysis. We're going to analyze it ourselves. And we have the import results summary. Shows us just a little bit of information about the program. So now we have our string of bytes that we can see here in the listing window. And we are going to simply run the NopEmulator script on it. So we click on the NopEmulator, and we're going to run the script. Now what we see here first is the type of analysis we want to run. There's different kinds, as I talked about earlier: beginning to end, start to end address, start address and length, longest, and full analysis. We're just going to do the default beginning to end for this to demonstrate how this works. Now it's asking us if we'd like to specify any registers to ignore. This allows us to customize our analysis and say, yeah, I don't care about this register, I don't care about that register, if we want to. In this case, we're not going to ignore any registers. And then do we want to set a specific value? In some cases, your analysis, it starts and ends at different values, but you don't really care, or you know that's supposed to be part of it. In that case, you can set registers to a specific value to better understand and analyze this shellcode, this binary, this byte sequence, more aligned with what your goals are, as opposed to the default or generic. We're going to leave them all defaulted to 0. So it ran, and it says this is an effective NOP. So let's walk through a little bit of what it did. So we look at the instructions here. We XOR RAX and RAX. That gives us 0, no matter what is in the RAX register. We have a check here, jump not 0. Well, this was 0, so we go ahead and jump down to the next instruction. We increment and decrement RAX. Again, up 1, down 1, RAX is still 0. Now we have a jump 0 flag that we need to check, which then sends us to label 11. Here, once again, we increment and decrement RAX, and then we test RAX. The test instruction is like a logical AND. So the logical AND of 0 and 0 is going to be 0, and then if it's not 0, we do a jump, but in this case it is 0, so we have a NOP at the end, and then we're done. So we can see, intuitively walking through this, yeah, this is going to do absolutely nothing. But we can run a full analysis, and we can see many cases where if we start at different places, then it could be something else. So let's go ahead and, instead of a full analysis, let's pick a different analysis. Let's do start address to end address. We're not going to ignore any registers, we're not going to set any registers. And the start address we're going to put is, let's put it as 5. We're going to start right here in this increment decrement instruction. And then the end address we're going to put as 11. So we can see here, we started at 3, or 5, I'm sorry, we started at 5, and we went to 11. So we only looked at these bytes. These bytes do not constitute a NOP slip. And that's basically what this tool just told us. So you can use those to customize your analysis when looking at this and say, what about just these bytes? Or what about from here to here? Or here plus 50 bytes? That's what the flexibility of NopEmulator has in order to show you how this works. Let's look at another demo. Let's instead look at some simple control flow that we might see in shellcode or byte sequence. So once again, we fill out the language, as Ghidra can't figure it out by just the shellcode. We don't need to analyze it, and we use a summary. So again, we don't know what this does. Let's go ahead and run our NopEmulator on it. We'll do the base, we'll do the default. And we're going to keep everything default. And we see here, we have an effective NOP. So what does this do? We're calling to address 9, which then rets, which returns us to instruction 5. We have a NOP, a jump to hex A, which is a NOP. So even with this, call, ret, instructions that move all over the code, NopEmulator is able to follow it and determine, yes, even with the control flow being changed, all of this is effectively a NOP. It does not change the state of execution. Now, if we could see this being a NOP another way. Let's say we start just at instruction 5 and go to the end. Still an effective NOP. Changing something doesn't always mean it's going to be not a NOP sled. There's potentially NOP sleds within this code that exist. Now, it's more reasonable to think that a longer one is likely the intended NOP sled that an attacker might be wanting to hit, but we don't have to assume that. Let's go ahead and clear this out and then run a full analysis on this to show what that looks like. So we clear out all the analysis that's been done, and let's go ahead and run a full analysis. We're not going to ignore anything. We're going to leave everything to default. Now, this blew up with a bunch of comments. That's on purpose. The whole point of full analysis is to say, hey, from anywhere to anywhere else, is this a NOP sled? So we can see here, the comment begin from 0 to 9 is a NOP sled. From 0 to A is a NOP sled. 1 to 2, 4, 5, 6, 8, 9, and A are all NOP sleds. From byte 2, 3, 2 to 9, 2 to A, NOP sleds. And then we have an ending. So it's like brackets. So we have a beginning from 1 to 2, or we have an end from 1 to 2, and we have a beginning from 1 to 2. These are the comments that encircle these bytes. And it goes, and this is done for every starting and every ending address here. Like I said, it can be pretty verbose, but this allows you to get as much information out of using this emulator as possible. Once again, let's go ahead and erase all of this. And let's do longest, because as I showed you before, the beginning to end was likely the longest, but there do exist other ones in between. So let's see if the analysis lines up with what our capability says. In this case, we're going to do longest. Leave everything default. And as you can see here, both in the logs, longest effective NOP from 0 to A, we also have the comments here, begin NOP sled from 0 to A. We can see here the longest NOP sled is the NOP sled from start to finish. So as one more example before we wrap up the recording, I wanted to do a more real-life example of what the capability of NopEmulator is. So I've grabbed a chunk of a PCAP that I've split out based on packet, and this packet was 290 bytes. I didn't want to pick one that was too long, but I didn't want to pick one that was too short either to demonstrate kind of what this looks like and how it works. So let's go ahead and take a look at it. Now, if we go ahead and just decompile this using Ghidra before we run our analysis, you'll see here that the instructions can be a little weird. And now you're seeing these red X's show up where it's having trouble decompiling. And a lot of these instructions don't look normal. These are not things you'd normally see in a valid executable. Now, that could be because it's encoded and it needs to be decoded. That's perfectly valid. There's plenty of shellcode that decrypts itself or decodes itself before execution. However, that's not the case here. So this would be an example of something a network IDS or IPS would have to process where you don't know if it's a good or a bad packet, and some of these bytes may or may not be valid. So let's go ahead and clear this. Now let's go ahead and let NopEmulator take a crack at this, and we'll do the longest analysis. Let's see if we can find the longest NOP sled in this packet. We'll leave it at the defaults, and this may take a few minutes, so if it does, I'll speed up the recording. Otherwise, we'll see what the longest NOP sled is in this. Now, as you saw, there's some updates in the Swing Update Manager. Without going into too much detail, basically when analyzing all of these bytes, given that not all of them are valid, there's going to be some issues where it has issues decoding the instructions, has issues parsing all of the objects behind the scenes. That's totally fine and normal. NopEmulator handles that, but Ghidra does display that there were unexpected exceptions. Totally fine, we can ignore it. Now we see here we have found the longest effective Nop in this packet from hex 4 to hex 6e. So let's go ahead and we can decompile there. We see we jump. We have a jump less than. The flags by default are not set. We now have a jump instruction to 6e. And we have a clear flags instruction. So while it seemed like it was a lot of bytes, in reality it was only a couple, three instructions that led to this NOP sled. But that's a perfectly valid NOP sled. You have something in here where you have all of this nonsense in here that doesn't actually do anything. It's there to throw off intrusion detection or prevention systems. It's there to differentiate from other exploits being thrown. That's all perfectly valid. And NopEmulator was able to find what it considered to be the longest NOP sled in this packet. So that's one example of how you can use it to actually analyze real-world code that doesn't fit nicely with the constructed assembly examples that I showed earlier. Thank you guys for hanging out and watching the NopEmulator video. I have all of the code and a README along with some of the shellcode and byte sequences uploaded to GitHub under Quantumite NopEmulator. This has a README discussing everything that I talked about here and a little bit more. Includes the types of analysis and even walks through a general usage similar to what this demo showed. If you have any questions or comments, feel free to submit issues or even do a pull request yourself. I would love for this to be a functional capability for all of those who want to use it, and hope you have a great day.